Okay, good morning, everyone. My name is Gennady Giyenka. I'm a faculty member at the Department of Geomatics at UAE College of Engineering. And now we are continuing our professional development seminars series. And the topic for today's series, presentation is related to surveying. Many of you will probably have these questions. What is the datum when you practically working with your construction survey, or even maybe you are a surveyor yourself? So the topic for today is a very interesting, specific to Alaska particularly, and that topic is tides, vertical datums, transformations for coastal engineering applications, particularly in Alaska. And I'd like to introduce our speaker today, and his name is Nathan Wardwell, and he works for the GOA Survey in a company based in Anchorage, Alaska. And he's doing this business for I don't know how many years. So he is one of the professionals who really knows the topic from the bottom up to the top of it. So Nathan, the floor is yours. Welcome.
Thank you, Gennady. So a little bit about myself. As Gennady said, my name is Nathan Wardwell. I'm a managing partner of JOA Surveys, which is a small survey business based in Anchorage, Alaska. And we specialize in measuring water levels in support of tidal datum determination. My background, I grew up in Anchorage, went to Alaska Pacific University. I got a bachelor's of science in earth sciences, worked for the United States Geological Survey in their field division, doing river discharge. Got my master's from University of New Hampshire at their Center for Coastal and Ocean Mapping. I did my master's work using global navigation satellite systems to validate the geoid model in the Bay of Fundy. I'm currently managing partner at JOA Surveys. I was chair of the Geomatics Advisory Board for the University of Alaska Anchorage for a few years. I'm on the steering committee for the Alaska Water Level Watch, and was recently appointed to a federal advisory committee called the Hydrographic Services Review Panel. And to be clear, today I'm speaking as an individual, not with my HSRP hat on. So, so my presentation is Tides, Vertical Datums, Transformations for Coastal Engineering Applications. Just a kind of overview of what I'm going to be talking about today. I'll kind of go into connecting different vertical datums and why. I'll go into the Alaska Coastal Mapping Strategy and Implementation Plan that is out for public review. Was released for public review back in November or so of 2021. I'll take a little bit of a deep dive into the accuracy of tidal datums, point out a few things for that anybody working in the coastal environment and using datum should be aware of. I'll do a brief overview of the Alaska Water Level Watch, and then I'll go into some emerging technology for measuring water levels that has very promising applications for Alaska. So, all right, to do storm surge modeling, inundation analysis, we need to integrate bathymetric and topographic data sets, right? And these data sets are referenced to different vertical datum. So the depths shown there in blue, those are referenced to mean lower low water, MLLW. NOAA's National Ocean Service basically maintains nautical charts. And then the shoreline on these charts are referenced to mean lower low water also. And for topographic maps, those are basically maintained by the United States Geological Survey. And the elevations are referenced to a different datum. It's called an orthometric datum. The current one being used is NAVD 88, North American Vertical Datum of 1988. The previous datum was NGVD 29. And in the next few years, they'll be moving to a new vertical datum. Now, one of the problems is the shoreline on topographic maps, it references the mean sea level shoreline. So, intertidal zone, there really isn't coverage, and we have a disconnect between the data sets because they're not on the same vertical datum. So if you're trying to create a seamless digital elevation model, you need to figure out a way to connect those datums to a common one. So just kind of bear with me here I'm going to just go over some basics on how you establish a tidal datum and get it connected, right? So yeah, I have a picture here of our tide gauge that's installed, right? And so you get, this is a pressure gauge measuring water levels. Those water levels are referenced to the orifice. The sensor is 0. So then you install a benchmark and you survey that benchmark in, so it's connected to the orifice. Yeah, the elevation, the difference between the tidal benchmark and the orifice. And you assign an arbitrary elevation of that mark relative to an arbitrary datum, typically called station datum. And it's a local datum specific to a tide station itself. And then now all of your water levels are relative to that local arbitrary datum called station datum. Now, once you've collected your water level data and you go to compute your datums, all your datums are now, your tidal datums are now relative to that local arbitrary datum. So you have, for example, mean high water and mean low water. There's a number of them, mean tide level, diurnal tide level. Now the challenge is, since those datums are relative to a local arbitrary datum, you can't connect them and relate them to datums at datum planes at other tide stations. You can compare the ranges, right? So like the ranges are the difference between mean high water and mean low water, or mean high water and mean low water. Because those are just ranges, they're not datum planes. So there's value in those datums, but there's more value if we can relate those tidal datums from location to location. And so with GPS positioning, we can now relate tidal datums to a common datum and all vertical datums to a common datum, right? And so a GPS satellite, all the positioning is referenced to an ellipsoid, a mathematical approximation of the Earth. And so you set up a GPS receiver on a tidal benchmark. You now get a precise position, 3D position of that benchmark, and you get an ellipsoid height out of it. And that mark is also tied to the tidal datum. So now you have, the relationship of that tidal datum to the ellipsoid, and you can do the same at another station. So then you can look at the variability of these datums spatially. To connect it to USGS and orthometric datum, so technically, to connect to NAVD88, you would need to do a level tie from a mark with an existing NAVD88 height, or you can use GPS and a geoid model. Currently, hybrid geoid models are being used in Alaska. It's the geoid 12B. In the lower 48, it's geoid 18. So with an ellipsoid height and the geoid model, you can access NAVD88. So now you have all of your datums connected. So one challenge or so is that, these datums, as I mentioned, vary spatially, right? And so you can't just determine the relationship of mean low water and the ellipsoid at anchorage and assume it's going to be the same at anchor point. It's going to be, so those are two locations in Cook Inlet, Alaska, right? And so this map here shows locations where I computed the mean low water relative to the reference ellipsoid, or realistically a reference datum NAD 83 2011. And so you can see, Composite Island out here near Southeast was 6.107, and that's in meters. And then you come out to Adak Island, 5.7. You work your way up the chain, Ahkun Island, Ahkun Cove, I guess, 16.6, right? So you get a large difference here. You start working your way north, in Barrow, Barter Island, it's now negative, right? So -2 meters. So a lot of spatial variability. Um, so NOAA put together a program called VDatum, and that is Vertical Datum Transformation Tool. And the whole intent was to create a software package that you could use to transform between ellipsoid, orthometric, and tidal datum, so that you
All
could
right, sorry to interrupt. It looks like we've lost the live stream here, so let's give it a minute.
Sure.
Because yeah, that just occurred probably about 30 seconds ago. And at first we were hoping it would just recover itself, but it doesn't look like it's gonna. So let's see if it gets back. All right. Okay, so yeah, if you could go back to what you were saying about 30 seconds ago for our audience, that would be great. I think we're good there.
I'm not sure exactly where we lost you guys, but I'll try to pick up somewhere around there. I mean, I was talking about the spatial variability of tidal datums relative to the ellipsoid, or realistically, the National Spatial Reference System, and the datum NAD 83 2011. So, and then I was gonna what NOAA was implementing was a program, or they started a program called the VDatum. It's the Vertical Datum Transformation Tool. And really it was there is a program to develop a software tool that allows you to transform between ellipsoid, orthometric, and tidal datum. So essentially you can integrate data sets on different vertical datums to create seamless digital elevation models, and you can use GPS to get precise positions offshore or along the coast and relate those to a tidal datum. So that program started in 2007, in October of that year. And they included coverage for Chesapeake and Delaware Bays, Mobile Bay, Florida, New Jersey, Narragansett Bay. And in 2008, they added some horizontal transformations and expanded coverage along the East Coast, added coverage to parts of the Gulf Coast. And in 2009, they expanded coverage to the Pacific Northwest and parts of California. 2010, that coverage was extended to North Carolina, or from North Carolina to Florida. 2011, they did some additional work in the Gulf to include Western Louisiana and Texas. And doing a lot of additional upgrades to the existing grids. 2012, there was a lot more updates to existing grids, so they were continuing to collect new data in those areas that they could use to better refine those transformations and update the grids to ultimately bring down the uncertainty in that transformation. 2013 to 2016, continued to update existing grids. 2017, extended the coverage to inland waterways in Florida. Like it was getting some good momentum. It was like, oh, hey, we don't just want this right along the coast, we want it in other areas. Continued to include more updates, throughout the time in 2018. That's included additional transformations, more software capability. And finally, in 2019, they extended the coverage to Southeast Alaska. And since then, they've continued to do some additional updates and doing a lot of work to better estimate the uncertainty. And at one time, they started out providing uncertainty estimates based on just a region. Now they're doing a kind of a spatial varying uncertainty, which is a large step forward. So you can currently, for work in Southeast Alaska, you can currently use this tool to transform vertical data sets among different vertical datums. I do want to point out, though, that the transformations in Alaska are handled differently than transformations in the rest of the country. So in Alaska, your starting coordinates must be in the IGS 08 reference frame, because they use a gravimetric experimental geoid. It's called the X geoid 17B. To transform to an orthometric datum, then they go to local mean sea level, and then they go to their tidal datums. In the rest of the country, you can start with IGS-08 or you would start with NAD83, which is what most users are going to start with because that's the official datum in the National Spatial Reference System. So just be aware that if you're going to use it for work, anything in Southeast Alaska, you'll need to start with IGS-08 as your initial coordinates. I think I speak to this why the difference, again, is because the experimental pure gravimetric geoid is used datum versus a hybrid geoid, which is essentially gravimetric data, but also that is warped so that the results match the official orthometric datum of NAVD88. So got to throw this map in here. This map shows all the tide stations as blue stars that my company JOA Surveys has installed throughout the country and US territories. Not all this was supporting the VDatum program. We started in 2003 or so doing tides work supporting NOAA and primarily the National Ocean Service for their charting program. To date, we've done more than 300 or so temporary tide station installs and built long-term stations throughout the state of Alaska to expand the network for real-time and long-term observations. This map also includes red dots on here, which are locations where we did survey ground checkpoints in support of the statewide digital mapping initiative. That was a program by USGS to update topographic maps for the entire state using elevation data from IFSAR. So we'll just kind of focus on Alaska here now. This map, I put this map together. It's a little out of date. Put it together a couple years ago. So the green stars are all the basically the active NOAA long-term tide stations. They're called NLONs. It stands for the National Water Level Observation Network. The yellow stars are locations where there's an existing tidal datum, and that tidal datum is currently connected to common datum, and like primarily NAD83 using global navigation satellite system observations, right? And so those are the sites where we know the transformation parameters between the different vertical datums. And really the intent of the map is to point out is like, okay, well, there's large gaps in our observation network for the active long-term stations and in our short-term datum determination to establish these transformation parameters. And I'll point out why that's important going forward, but I'm sure as any coastal engineer is going to know, we have very dynamic tides throughout the state. It all depends on where you're working. Here's a simple plot showing simultaneous water levels at all of the red, green stars on that map. And large difference in the tide range and tide type. It all depends on where you're working. So you can't assume that active station is going to represent where you're working along the coast if you're depending on how far away you are. So here's where I'm going to take a slightly deep dive into tidal datum accuracies. So NOAA computes tidal datums at short-term stations, and the short term is essentially realistically defined by anything that's been installed for less than 19 years. Typically, it's short term. We're collecting 3 months of data to do a short-term determination of a tidal datum. So they compute datums using 3 different methods. It's called the first reduction, TBUIT simultaneous comparison, and the monthly mean simultaneous comparison. And now the datum accuracy improves by using as long of a data set as you can possibly use, and then using a control station for simultaneous comparisons to scale the datums to a long-term equivalent. So those green stars in the map I showed previously would be considered our control stations. They have authoritative tidal datums and simultaneous water levels that can be used to scale observations at a subordinate station where you're collecting a shorter amount of data to get your datum. Now, this table shows the generalized accuracies of datums computed using simultaneous comparisons, primarily that monthly mean simultaneous comparison approach mentioned in the previous slide. This is from some work done by Swanson in 1974. It shows 3 regions. So this is the East Coast of the US, the Gulf Coast, and the West Coast. We have the series length, so 1 month of data, 3 months, 6 months, 12 months. And then the accuracies in centimeters and feet. And I referenced the publication that it comes out of at the bottom. So the NOAA special publication, NOS Co-ops 2. So like in general, they don't have this for Alaska. So I tend to use that West Coast. And you see at 1 month of data, when you have a control station, your accuracy is about 4 centimeters at 1 sigma. After 12 months, it cuts it in half about. Now they did do in 2014, they did a similar analysis, but instead of looking at accuracies using control stations, so simultaneous comparisons, they looked at the first reduction approach, also known as FRED. So essentially, with a FRED, you're simply taking the designated tides. So you take all of your lower low tides and you average them, and that's mean lower low water in a simplified manner. That's what it is. So there's no scaling to a long-term equivalent. So they broke it out into different regions, and then again by the series length. So Southeast Alaska, Gulf of Alaska, Aleutians, Bering Strait to Beaufort Sea, and just all of Alaska. And so, if you have 1 month of data, when you're computing a datum, you don't have a control station, the standard deviation of that is going to be 11.5 centimeters. It takes 12 months of data to drive that down to 4 centimeters. At the bottom, I have the reference for the technical report that this information came out of. So just kind of highlight that if you have a simultaneous comparison, so a control station, after 1 month of data, you have an accuracy of about 4 centimeters at 1 sigma. Without a control station, it takes a year of data to drive it down to that same level of accuracy. And collecting a year of data in a lot of Alaska is challenging because of sea ice. So now I'm going to go into some of the metadata on tidal datums and where you can learn more about the length of the data series so that you can figure out, get an idea of the accuracies of the datums that you're working with, right? And so the authoritative place to go is NOAA Tides and Currents. I have the URL there at the top. This is the map. And then where I like to go is I look at the tidal benchmark sheets, and that really has the information that is valuable to me to tell me how the datum was computed and how much data was used, what control station was used, and what epoch the data is referenced to. So here's an example tidal benchmark data sheet for Anchorage, Alaska. And so you see it on the left, that red box outlines kind of the upper area where I'm going to say it has the metadata about the tidal datum computation. So it shows the length of the data series, it shows the time period, it shows the tidal datum epoch, and then the control station. So for Anchorage, it's 19 years. They use a sporadic amount of months throughout those years. That may be because either the gauge wasn't reporting for some months, so they don't have that data, something along those lines. They report the tidal datum epoch of 1983 to 2001, which is the current national tidal datum epoch that is used for all tide stations. NOAA uses a 19-year period of time to define a tidal datum epoch. That includes the 18.6-year metonic cycle, But then they round it up to an even year to include the seasonal effect, so there's no seasonal bias in that additional year, or by using partial year. And then we see it was computed using a first reduction, and I know that because there's no control station listed in the metadata. Now the next section down, that shows all of the tidal datums reference to mean low water. And then the next section down, that shows all the published tidal benchmarks for that tide station with elevations above mean low water and mean high water. And they provide those primarily because all the depths on a nautical chart are referenced to mean low water, and any heights on a chart are referenced to mean high water. So coming back to this metadata here, right? So for, the Enlon, the active tide station in Anchorage, is an active one. It's been around for, I'm not sure how long, but at least 19 years. We know the data was computed from 19 years of data. So theoretically, there's no error in that data, right? It spans the entire national tidal datum epic. But the center of that epic was essentially 30 years ago. So basically that datum is based on mean sea level 30 years ago. And we know that the ocean's not stable and the land's not stable. So mean sea level 30 years ago in Anchorage is not representative of what it is now. And in other areas that are more tectonically active, like in Southeast, it'd even be more so, be off more so. Here's Seldovia, Alaska, another Enlon station in Cook Inlet, south of Anchorage. The datum here, you look, the length of the data series is computed from 19 years of data. However, the epic is defined as 2012 to 2016. And that goes to what I was just talking about rapid land movement. So in areas where the movement of land is the vertical movement of land is so rapid that it exceeds some threshold that NOAA has, they use a modified procedure. And that modified procedure basically is they use that 5-year epic to define mean sea level, but then they use the 19 years to define the tide range, if they have 19 years of data. So that essentially that gives a better, more current representation of where the datums are in reality. So now for like a subordinate station or a short-term station. So here's Homer, Alaska. The historic name of the tide station was Coal Point. That's why it says Coal Point at the top of the data sheet. But that's that right there. We actually installed this station in 2018. So the datum is computed from 3 months of data we see. They show the time period, so September 2018 to November of 2018. We see that the control station was used, and that was Seldovia. And so the tidal datum epic for the datums in Homer are the same epic as the control station. So it's 2012, 2016. If Anchorage was used as the control station, the epic would be the 1983 to 2001 epic. Now here's another example, this was kind of interesting, but definitely something to pay attention to. So here's a Luckenock on the Yukon River in Alaska. We actually installed this one in 2021. So the datum at this site was computed from 2 months of data. It shows the time period. There's no control station that was used. So we know it was computed using the method of first reduction, and the error in that datum is higher. I automatically know that because there's no control station used. But not only that, if you see the tidal datum epic is stated as 1983 to 2001, which, technically that's not possible because the data was collected in 2021 and it wasn't scaled to a long-term equivalent, bringing it back to 1983 to 2001. So just a little something to be aware of when you're looking at these data sheets. So here's the map of the existing Enlon stations in Alaska. It doesn't show all of them because of the way the map is, but it shows how many we have. I think it's about 27 right now spanning our coasts. And the major gaps in the network for which results in larger error in the datums in areas between in those gaps. Those large gaps are, YK Delta, Bristol Bay, and the Arctic, Western, Northern Alaska primarily. Very challenging places to install long-term stations. I mean, that's the reason why. And then, so this is a map of all of the continuous GNSS, so global navigation satellite systems, or like GPS stations throughout the world. I highlighted just Alaska. Really great site, Nevada Geodetic Laboratory GPS networks map. I like this site. You can click on one of the dots and automatically see a plot of what the movement at that site is. So like this plot shows east at the top, north in the middle, and up at the bottom, right? And so using the long-term stations where there are sea level trends published, so you get relative sea level rise, and then these continuous GPS sites, you can get vertical land movement. And so you can start looking at, absolute sea level rise and trying to figure out, well, why is is it relative, all the Enlon stations are relative sea level rise because the water levels are relative to the tide station, and we're not monitoring the movement of the tide station, and the tide station is moving with the land. But we have the GPS installs that allows us to get that tectonic signal to then extract it to. And so I'm just showing you an example here of Skagway, Alaska. The map in the left, the red star shows Skagway. The plot at the bottom left is mean sea level from about 1940 to 2020. It shows the relative sea level rise of minus 17.7 millimeters per year. And then the plot on the right is the height east and northern for the continuous GPS site at that in Skagway. It's less than 10 kilometers away. And you can see the vertical land movement is in the opposite direction, 16.8 millimeters per year. So most of the sea level rise, relative sea level rise in Skagway is due to uplift in that region. And I'm just highlighting, so NOAA did come out with a large report recently, a great report on global and regional sea level rise scenarios for the United States. And this is highlighting this map. I haven't looked at it in detail, but essentially these 4 charts, right? The one called labeled A, it shows the vertical land motion rate estimates that NOAA was coming up with, and then B is from GPS, and then the C is the difference. And the reason why I'm including this, what jumped out at me right away is when you look at the difference plot, there's a lot more variability in Alaska than you're seeing on the East Coast and the Gulf Coast. I haven't dug into the report enough to know exactly what they're looking at, but we have a lot of shaky ground in Alaska, to use Jeff Freimüller's phrase. So the Alaska Coastal Mapping Strategy Implementation Plan, I'll start going into that a little bit. This came out, as I said, I think towards the tail end of 2021. It has lots of objectives, goals, plans, and milestones for the state. I'm gonna highlight what's relevant, primarily relevant to water levels, datums, and the geodetic infrastructure for the state. So objective 2.2 is upgrade Alaska National Spatial Reference System components to support mapping data acquisition. And then they go into defining milestones. So there's 5 milestones identified for this plan. So the first milestone is to produce a geoid model for Alaska to improve vertical data positioning accuracy. So that geoid model gets us from an ellipsoidal datum to an orthometric datum. NOAA's been making great progress on this. We see the leads and the supports and the performance indicators and the year goals, right? So the goal for the remaining areas of Alaska gravity is October of this year. And having GravD, which is their program for gravity, fully incorporated into the gravimetric geoid model by 2025. The goal 2.2 or milestone 2.2.2 is establishing foundation cores in Alaska for active NSRS control and international terrestrial reference frame alignment. By October of 2023, they want to get 5 new cores in Alaska, and these are providing the foundation for NSRS. The next milestone is conducting a cost assessment to establish improved geodetic control and relative sea level trends at Alaska water level stations. So coming up with cost assessments for addressing the gaps in that network of green stars that I showed around the state, and then co-locating continuous GPS stations with NLON, so we can be looking at the multiple signals of sea level and tectonics. Goal 4 is establishing comprehensive Alaska VDatum coverage. So getting full coverage of Alaska in VDatum so that we can be doing these transformations throughout the rest of the coast. And with the objective of those models being fully developed by 2028. So NOAA is actively installing additional short-term stations in the state to collect this data now. And then establishing preliminary real-time water level network to support mapping activities in communities where there are NLON gaps, and essentially using alternative technologies that would get water levels at communities, but it doesn't meet the accuracy standard of an NLON, but there's still added value to fill these gaps. And that effort is being led by by Alaska Ocean Observing System with support from NOAA and the state of Alaska. So a little bit about the Alaska Water Level Watch. As I mentioned, I'm on the steering committee for that. We have a web page here, and I highlight this. We have a build out plan for real-time network in Alaska and build out plan for tidal datums. If you go to that story map, you can learn more about the build out plan. This is kind of an overview of the plan. Here is the map of tidal datums. They're color coded by what's completed, what the priorities are, where we want to go. We really started out with prioritizing communities because that's where we need the information at the very least. That's been now expanded to remote locations so that we can get the additional information that can go into VDatum. And here's the map for the kind of the build out plan for the real-time network. It shows what's operational, what needs work, what's planned, and then in addition to that, so we have we're trying to encourage people to share their water level data since it is sparse, but it is of value for other users, and so you can go to the Alaska Water Level Watch page, and there's a link to fill out a form to submit your data. And then it'll be accessible through this real-time data portal that was put together by Axiom and managed by Alaska Ocean Observing System. So I think I'm running out of time here. So quickly, I'm going to get into some emerging technology, which is the part that really gets me excited. So we've been doing a lot of work with GNSS reflectometry recently. So essentially, using multipath signals from global navigation satellite systems that are reflected off the water surface to then determine the height of a GPS antenna above the water level and ultimately getting the tide. So here's a picture of a GPS continuous site up at St. Michael, Alaska. That was kind of one of the ones that started it here in the state installed specifically for that purpose. Along with positioning, there's been additional work being done in Wainwright, Uktiavik, Egegik, Homer, Whittier, Seward, and it's all been kind of like testing research, and it's in temporary short term, except for Uktiavik. That one is the intent of that one right now is long term. So kind of highlight the value of this. So in, I don't know, 2014 or so, we built an NLON station which is, a long-term permanent station for NOAA in Unalakleet. Unalakleet's about 47 miles northeast of St. Michael in Norton Sound. And so the only place to build an inland station in Unalakleet where it met all the requirements of NOAA, because the vertical stability of the sensor is the highest priority, is tucked up behind this in this lagoon on this river where there's a seawall. And so we could weld the orifices to the seawall that's shown in the picture on the bottom right. But it's not observing the full ocean tides, and as I'll show here in a little bit. Now, for the reflectometry site in St. Michael, it's right on at the point, and you can install it anywhere because it's a method of measuring water levels using a remote sensing technique, essentially, that's passive and measures the water levels at an oblique angle. So you don't have to be right over the water level or the water. So now here's a plot of water levels using the reflectometry analysis of the data at St. Michael. And you see we get a nice tide curve. This data we processed using it's called a spectral analysis, an algorithm developed by Christine Larson. We process the data using a technique called is inversion method, using an algorithm developed by David Purnell, and that's the red line here. So we see a really nice tide curve here that we're getting in Norton Sound at St. Michael. Now, overlaying that tide curve, here is the data from Unalakleet. And so this black line is the data from the end-line at Unalakleet. And we clearly see that we're not fully observing the low tides at Unalakleet, primarily in the winter months. We're just getting the high tides. And so it doesn't provide suitable datum control at all the time, and definitely not all the time during the year. And so by using this reflectometry, we're able to expand the opportunity of where we can get full range tides, full ocean tides throughout the state. Because we're not only measuring the water levels, but we're measuring the precise position of the antenna that we're referencing those water levels to. So we know the stability of the sensor, and we get tectonic signal, we get water level signal. And that is my presentation for today. I appreciate everybody that was listening. I'm gonna have my contact info there at in the upper left if anybody wants to reach out.
Okay, Nathan, thank you very much. I'm hoping that the audience can hear me now. And yeah, I think that's, yep, should be now. I think it was a great presentation, and I have a couple of questions actually for Nathan here. First question is, my understanding is that we need a substantial number of stations to monitor the heights and the tides. How many do we need per mile, per 10 miles, to actually get the reasonable estimation of the tides? How many tide stations are in lower 48 per mile or per 10 miles, and how we are deficient here in Alaska in that particular way?
That's a great question, and it's a question that people have been trying, and it's not an easy thing to answer. And people have been trying to answer that, because like if we can quantify how many stations we need, we have an end game, right? We have a goal. Like this is what we need, right? We can let's go get funding to get these in there, because and then once we get that, that's where we'll be. The challenge is you can't just say, oh, we need a active end-line station every 30 miles, right? Because the tidal characteristics could change throughout that region and in between. So you may not be, if you have an end-line station 30 miles away, maybe it's not suitable for datum control in between, or maybe it is, and so like you can have a larger range spread of those active stations that are used for sea level trends and datum control. But then you fill in those gaps with the short-term observations to get those datums in between. So then you you nail down those transformation parameters in between to get the full coverage for like VDatum program, knowing that, okay, well, we don't need to provide active water levels there real time to support safety of navigation or sea level trends, right? And that sort. And it's, I had a slide, I didn't put the slide in here, and I forget the difference in the stations per mile for Alaska versus the rest. It's obscene though. It's pretty poor.
Okay. Until we get the questions from the audience, I think that we have questions in the chat. So I have this opportunity to ask another question for you here. So in the Alaska Mapping Initiative, the Coastal Mapping Initiative, is there any provision to set up tide stations or tidal observation stations in the prospective area of the development? My understanding is that you really need to have at least 1 year of observations. 3 months, it doesn't really need. It is not really it doesn't give you the substantial details about the accuracy of the tide. I will put my question that way. Is there any strategic planning or relationship to the Alaska state strategic development where the stations need to be set up in terms of to provide the long-term decade or 2-decade measurements?
Yeah, I mean, great point, right? So a 3-month observation isn't going to give a coastal engineer the information they want, right? And I mean, the challenge is right now using the accepted technologies for an inland. The only places you can put these things are where there's a dock or a seawall, right? And you need some fixed coastal infrastructure. You need power. We use GOES telemetry, so you don't necessarily need internet, but power is the primary thing. And then you need something super stable to install that's gonna to mount the sensor to, and that is gonna withstand ice, right? So Nome, there's a port there with a seawall. You can weld the orifices to it, and it's stable. You can monitor the stability. We do differential levels at these stations every year, so we know the stability of the benchmarks and the sensor. A lot of the places where there are existing infrastructure suitable for that have been used, right? There's like Naknek, we have a station that we installed for Alaska Ocean Observing System. Doesn't quite meet the NLON standards, but we're showing that we can do long-term observations there. That would fill a gap in Bristol Bay, a needed gap there, if we eventually turn that into an NLON. But as you start working your way north, there's nothing stable to mount it to, right? Unless you're doing some directional drilling to get below the sea ice and have a sump well, with some approach that's used in the Great Lakes. That's what they use in the Great Lakes. Or we start looking at emerging technologies, and we're looking at these approaches of like reflectometry, right? And so there's limitations of reflectometry. You're only truly getting water levels when it's open water conditions, right? You're not getting the water levels when there's ice there. You may be seeing what the surge is doing or the set down is doing, and there's still value in that. But if we're not looking at these emerging technologies, we're not going to get there.
Okay. I think that Nathan, do you see the charts? Yeah.
Yes, there is a question from Adele Huppel. In the slides about Skagway, I thought the graph showed the water level decreasing and the land level increasing. The water is increasing though, as you mentioned. I must be misunderstanding.
No, that is what that plot was showing. So it showed I could go to the slide, but it showed the relative sea level trend from the NLON station there in Skagway. And so that trend was a downward trend, but it's a downward trend because land is moving up. And that vertical movement upwards of the land we can show by the from the continuous GPS site. So we're getting a vertical position from that on a daily basis, a new position. We see that trend over years. So we can see that the majority of the water level trend there that we're seeing that's relative to land, again, relative to land because the tide station, it's relative to the tide station and the tide station is moving with the dock or the land. It's a downward trend, but that doesn't mean that that's what, there may still be an upward trend in sea level. I don't know for sure, but you have to account for the land movement if you want to start looking at things like absolute sea level trends. I think I answered the question. If I didn't, then
well, it sounds like the land mass is rising, right? And the water level is also rising, but the land mass is rising faster than the sea level is. Is that more or less it?
More or less, yes.
Hey, that looks like all the questions we had in our chat.
Oh, okay, so then I can fill a few minutes of our time with another my question that I have for you. And again, that the question is related to the new technology that you were talking about the last slides, related to reflectometry. I think that I said it correctly, that use the multipath reflection from the GPS signals, right? So, and the few slides at the very end of it indicates that there is quite a bit of a difference between the readings of the stational regular classic gauge and the readings from the interferometry here, or reflectometry, sorry. I've noticed on that particular plot that the difference exists not only between the recorded values of the tides, but also between two methods which are used to compute the tidal the differences here. And I've noticed that particular discrepancy can be up to, say, 25, 30, sometimes centimeters, but that's substantial, right? So is there any particular study that indicates that the new reflectometry method is reliable outside of Alaska? I understand it should be somewhere, but based on the slide, I have a feeling that it may not be always reliable, maybe in Alaska, or is there any studies saying, yeah, that's absolutely reliable method and we need to use that?
So, yeah, great point. With the reflectometry method, you got to understand it's not as accurate as a traditional tide gauge. That's not, at least not now, and that's for sure, right? And so you're getting a lot more noise in the measurements. There's a lot more uncertainty in where the water level is. There's this approach for doing tides. I think it was originally started around 2012 or so. So there's a number of publications out there that show it as a viable approach for getting sea level. But with anything, you understand the limitations of the approach, right? And so like, there isn't one tool that's gonna work or one sensor that's gonna work for getting us water levels throughout the state. There's multiple tools and multiple applications for those tools, and you need to figure out which one works for the scenario, right? And so that's kind of the point that I'm trying to drive home here, right? It's like we can't install a microwave if we don't have a dock, right? We can't install a pressure gauge if there isn't a dock, because it's gonna move. And once the sensor starts moving, the data accuracy reduces, right? It's not as quality anymore, because it's all relative to that sensor. With reflectometry, we have additional noise, additional inaccuracies in the water level measurement, but we're precisely measuring where that sensor is on a daily basis. We're not getting that from a traditional tide gauge. So we know how stable it is, we know where it's going. So we compromise on the accuracy of the water levels, yet gain substantially on understanding the movement of the sensor. And there may not be any other option in that location, right? So I don't know if I fully answered your question, but
Yeah, understandable. So that leads to maybe I have too many questions. Do we have anyone?
I love it, man. That's great. I'm glad you have questions.
No.
Go
I'm
on
asking, is there
ahead.
any...
We don't have any more on chat right now, so please proceed.
Okay, good. So from the practical point of view, what accuracy is needed? Because we're talking about the applications, right? So there is a theory, there is the filtration methods, there is some kind of Fourier analysis, name it, it's all signal analysis, great. But what accuracy do we practically need for applications? Just coastal engineering. 1 centimeter, you said, well, to reach a 3 centimeter accuracy or 4 centimeter accuracy, you need 1 month in the lower 48 and 1 year here in Alaska. Right. So what accuracy do we need?
I mean, that's a great question. I mean, I'm not a coastal engineer, so I don't know. I mean, that's something that I'd be interested in hearing from a coastal engineer. What I can say is, I mean, I was literally having this same discussion with NOAA right before this presentation. And we were trying to figure out, because we're trying to operationalize this approach. And it's like, well, what would be a target accuracy level that we should achieve? And there wasn't a clear answer. Something that did come up though was like, so the level of accuracy that's trying to be achieved for supporting hydrography is better than 10 centimeters at 95% confidence. So knowing your water levels to that is acceptable for hydrography. So if we could drive the air down on these reflectometry approaches to that level, then it might be acceptable. And then something else to consider is, okay, well, are we using the approach to measure water levels only as the product, or maybe we're just using it for datum determination, because there's a lot of filtering and averaging that then happens to those water levels to drive thousands of measurements down to one single data point, which then will reduce your, you may have more error in your measurement, but as long as that's a random and it's not a bias in the whole thing, you may still have a very reliable and accurate datum at the end of it.
Yeah, I think that all makes sense, including that particular aspect of because it's all related to the geoid itself, to the gravity forces that we have around. So the geoid itself is not really fixed like a frigid thing. It's also moving. So that relates to the accuracy of the geoid itself. It relates to the accuracy of all local gravimetric measurements, if you have them. You mentioned that we have the geoid 12B, I guess that's what we use there. But anyway, so that links to a very interesting discussion, I think, for most of the coastal engineers who need to know the local level of the water for the task they have in hand. So I think that it was really interesting presentation, that at least in my opinion, from the geomatics point of view, lots of information that I've learned myself. And I think I really enjoyed that. Thank you very much, Nathan. And
I think that I'm glad you enjoyed it.
Yeah. And I think that would actually be close to what we have today. We have 1 minute to go for the live presentation that we have now. And for those people who wanted to use that opportunity to be here and get 1 hour for your professional development hours, you might need to go online and fill in the questionnaire, and you need to have a password, right? So the password is actually on the screen somewhere, and I'll get you guess for a few seconds what the password would be for today's presentation.
Okay, transformations all lowercase.
Transformations all lowercase. You can really see it on the screen. It's all transformations from one system coordinate datum to another one. So thank you very much for being with us this Friday. I'd like to thank you, Nathan, one more time. I'd like to thank the technical support who were able to arrange all these things. And I think we are all done for today. Thank you and have a great end of the Friday and the weekend. Thank you.